This is a biology class right now for you?
It's chemistry, actually.
Chemistry. Okay, fine. So last class, what were we doing, Anu?
Last class, we were doing the different types of bonding.
And have we completed the different types of bonding?
We did metallic, ionic, and covalent.
Okay, good. Then what do you want me to do today for you?
Dave, 1 second. I've
Yes.
written it down.
Yeah.
Could you do time of flight?
Sorry?
Time of flight questions.
I didn't get you, please. Can you repeat that again?
Time of flight, if...
Time of flight.
Yep.
Okay. Is it regarding the spectroscopy?
Yes.
Okay. Okay, so we'll see the time of flight, which is regarding the mass spectrometer. This class. Whose class? Okay, so have you done this in school?
Yes, I've done it, but I don't understand it fully.
Okay, fine. Tell me something about this, what you know.
It's a method used to find the abundance and mass of an isotope of an element.
Okay, to find the isotope of an element. Okay. For this, I would like to draw a diagram for you that will make you understand better. Okay. Okay. Fine. We'll start. Okay. Now this is the point of extract. Okay.
Okay.
This is extract. There is acceleration. This is the field, free and this is the detection part. Okay.
Okay.
Extract. Okay, now there are electrons over here or elements over here which is there present in this extract. Just imagine there are two types of electrons which are going to emit from here. One and two, right? Now I need to release these elements, and these elements need to come till here so that I can detect over here. Okay, these are the two samples. Okay, from the extract point, they have to pass through the acceleration point, they have to come to the field free drift, and they have to come till the detection point wherein I can identify my samples. Spectrometer. Okay, now how are they going to travel from here to here? Are they going to travel both in the same speed, same velocity, or both of them will differ?
They will differ because of their masses.
Because of their masses. Very good. But here we cannot judge looking at them which has a lower mass, which has a higher mass, right? So we need to release these elements, and these elements or the samples then can move and come and reach the detection point. Once they come and reach the detection point, we can judge them according to the velocity or acceleration, whatever falls into space. Okay. First thing, what are we going to observe here is the electrospray ionization. Okay. Now the sample is dissolved in a volatile solvent. Okay, this sample which we are talking about, they are dissolved in a volatile solvent. I'll write that. And later they are injected through a fine hole needle at a very high pressure. So there are some fine hole needle over here, and through that they are being injected at a very high pressure. Okay, so this sample, they are being injected Next, what is happening here is, as the solvent is evaporating, now we have said that the sample is dissolved in a volatile solvent. Okay, tell me, what do you understand by volatile solvent?
It's easily evaporated.
Okay, which is easily evaporated. Now, third point, what we see is, now because the solvent is evaporating, it is subjected to a high voltage. When we are giving them with a high voltage, what is happening is they form positive ions. Okay. So electrospray ionization is a process where the sample is dissolved in a volatile solvent. They are injected through a fine hole needle at a very high pressure. What is happening? Because we are taking a volatile solvent which is evaporating easily, it forms or it is subjected to a high voltage, and this is resulting in positive ions. When do substances or samples form positive ions? Can you help me with this? When can a substance or an atom can form positive ions? Or why do they form positive ions?
Or by gaining a proton.
Gaining a proton, very good. But when we are talking about Electrons, we have to mention that they are losing electrons, okay?
Oh, okay.
Generally refer to gain or the loss of electrons, right? So we'll
Okay.
stick on with that only. We'll talk more about electrons rather than protons. Clear?
Okay.
Okay. So that was electrospray ionization. Okay. Second we'll see is acceleration. Okay. Now generally tell me, what do you understand by the term acceleration?
Acceleration is they are accelerated using an electrical field.
Sorry.
They are accelerated using an electrical field, so then they all have the same kinetic energy.
Okay, kinetic energy. Okay, they are accelerated by the same electric field. So acceleration, I can say they are the positively charged particles. What is happening here is positively charged particles. One moment, please. One moment, Anu.
You are now muted.
Class சரி பட் நான் ஒரு இது ரெக்கார்டிங் ஆகுது அதுக்கு தான் நான் டென்ஷன் ஆகுது பஸ்
You are now unmuted.
I'm sorry. Okay. So I was telling you these are the positively charged particles. Okay. What is happening is these positively charged particles, they are accelerated by the electric field. Okay. There are some positively charged particles which are accelerated by the electric field, and now what happens is each of them create each type of ion with the same kinetic energy. So is kinetic energy involved with acceleration?
Yes.
Okay. With the same kinetic energy. Now if suppose I give you, like if the ion has a very high mass, okay, so what will be with their acceleration?
So it'll show that they all have the same show their positive.
No. You remember the early part when we spoke, it depends upon the masses on how fast or how frequent they are going to travel here.
Oh, okay.
Okay, now this ion has a very high mass. So how will be their acceleration? Will it be fast or will it be slow?
It'll be faster than the other one.
That means the one with the higher mass will be slow, right?
Oh, so okay.
The ion has a high mass or it has a high charge, okay? I'll write down.
Okay.
So whenever an ion has high mass or charge, what is happening is they will be accelerated less. You understood this? What is happening?
Yes.
Yes. Why? Because they have a high mass. The movement will be much slow, right? So this is because of the acceleration. Clear with this part? You understood what is electrospray ionization?
Yeah.
And you understood the concept of acceleration over here?
Yes.
So if you want to note it down, then I'll move on.
I finished noted down.
You're done? Okay. Moving on. Third one we are going to talk about is ion drift. What is an ion drift, or what is happening with an ion drift? Now, this is the field free drift, right?
Right.
Substance is coming, it has passed through the acceleration point, right? This is the electrospray ionization we saw. Next we saw is the acceleration part. Then we are coming to the field free drift, okay, this part. Now what is happening here is these ions, they leave the electric field and are allowed to drift to it. That means they're allowed to move here freely, anywhere, any position, okay. So as the speeds are exactly same, when they are released together, their movements are somewhat same. But when it is accelerated, what will happen is it starts moving. I mean, only when it passes through the acceleration, because of its high mass and charge, what is happening? The movements will differ, right? If this is the high one, this is the low one. This is a high mass, this is a low mass. If it is a high mass, once it reaches the acceleration part, it will slow down, right? It will slow down and it will move a little slowly here and there. But since this has a low mass, once it is crossing the acceleration, it will move in a fraction of a second. Yes,
Yes.
allowing them to separate when they enter this field drift. Okay,
Okay.
so this is the ion drift. What is happening is ions leave the electric field. They are allowed to drift through it. Initially, both the speeds are same, right? When they are released through that electrospray ionization, the speed is same. Initial speed are same. When accelerated, they are allowed to separate, right? They are when
Right.
allowed to separate. Why? Because these ions, they have different mass and charge in them. Got it? What is happening?
Yes.
Okay. Last what we have is the detection one. Okay. Generally, detection means the final stage, right? The final stage of what have we detected, of what or what result have we got. So what is happening here? Now those with a low mass or charge ratios and higher speeds, they will reach the detector first. Am I right? Because higher mass, they tend to come in slowly. But the ones with a lower mass, they reach the detector first, right? This is what we saw here. If this is
Yeah.
with the low, they are going to reach the detector first. The higher one, it is drifting freely, so it will come and reach here slowly. So now there is a current. A current is created when the positive ions hit the detector. Okay?
Okay.
A current is created when the positive ions is hitting the detector, and this is measured along with the time of flight. Okay? So you understood what is happening? So
Yeah.
detection, what is happening with detection? Those with low mass or charge ratios and higher speeds. Speed also matters over here, right? It will
Right.
reach the detector first. what is happening? A current is created when positive ions hit the detector, and then it is measured along with time of flight. You understood this part? So you understood all the 4 stages of what is happening? The electrospray, the acceleration part, the field free drift, and the detection one. Okay?
Okay.
Clear?
Yes, clear.
You have noted down?
Yes, I've noted it down.
Oh, good. Now we'll move on to mass spectrum. Okay. Now again going back to the diagram. Now, so we have emitted the samples. Okay, they have moved past the acceleration. They have come to the field free drift, and we have detected. So once these ions have been detected, what is happening? A spectrum is being created, right? A spectrum,
Right.
and this is then simplified into graph, right? Whenever we are doing mass spectrometer, we always detect it, sorry, with the help of a graph. Yes? So how will
Yes.
it look like? So we'll draw a graph here. And there will be values, right? So each of them will have different values. Let's start with the value. Here will be the my y-axis with relative abundance. You know what is relative abundance in isotopes?
Yes,
Okay.
it's combining all of the isotopes masses.
Yes, relative abundance percentage, and here will be the mass or the charge of isotopes. Okay, here will be the mass or the charge of isotopes. Now I'll put the values over here. Let's start from 84, 85. This is just my assumptions, okay? 80, 87, 88, 89, and 90. So possibly this might look like this. Okay. So 86, my value was this much. 87, it was still decreasing, but 88, I have an increased relative abundance. Okay?
Okay.
What does this mean? Now this spectrum is the I have drawn of the element called strontium. Okay, this is the element strontium, and according to strontium, they have 4 isotopes. Okay, with the mass number 84, 86, 87, and 88. Okay, that is the reason I have drawn this. I've started with the value of 84. Okay, 84, 86, 87, and 88. What element I'm talking about?
Strontium.
About strontium. Okay, and there are 4 different values, 4 different isotopes of different mass: 84, 86, 87, and 88. Now what is the relative abundance of each of them? Okay, 84 is present with 0.56 percentage. 86 is there for 9.86. 87 is there for 7 percentage, and 88 has 82.58 percentage. So can you see the rise? 86 is 9, so it is going up. 87 is 7, so it is down. And 88 has the highest relative abundance, that is 82.58 percentage. You understood the graph over here of strontium?
Yes.
Okay. Now the mass or the charge of these isotopes all are having positive charge. Okay, all of them are having positive charge. Now using this data we can work out to find out the relative molecular mass. What is relative molecular mass?
That's the simplified number
Simplified number of,
of an element's mass.
okay, something else which we can add it up to the definition. Nothing? Okay.
No.
Relative atomic mass. Okay, this is relative molecular mass. Okay, there is something called as relative atomic mass. Relative atomic mass. You remember with this symbol AR? Do you know what is relative atomic mass?
Sorry, the screen is just frozen.
Can you see what I'm writing it down?
No.
No? Okay, what is the last thing which you saw or I have written it down?
You've just written relative molecular mass, and after that,
Relative
it's
molecular mass. After that, nothing you can see?
no.
Here, now?
Should I try refreshing the
Yeah,
page?
please try refreshing it.
You are currently the only person in this conference.
I see that now. Thank you.
Yeah, okay. Okay. So we're talking about relative atomic mass. Now, strontium has 4 different types of isotopes, right? And each of them
Right.
has different abundance. Now, what value should I write for strontium if I'm going to put it there in the periodic table? I should write only one mass, right? One particular mass. So
Yeah.
which of them should I consider? 84, 86, 87 or 88?
88 because it's got
Why
the most.
88?
Because it's the largest percentage.
It is the largest. But each of them have a share of them, right? Each of them are actively participating in this mass value. So what are we going to do here is we are going to take the average value.
Okay.
So relative atomic mass, the perfect definition for it is weighted average masses of the isotopes on a scale of which all carbon 12 atom has a mass of exactly 12 units. So basically what we do is we compare it with a carbon 12 atom. Okay, carbon, if you see, it has atomic number at 6 and mass 12, right? Only because it has the double value of it, we always compare our elements with the carbon atom. So you understood what is a relative atomic mass?
Yes.
Yeah, I'll give you one simpler example, okay? Not going into detailed form. Let's take a simple example. Let's take that of chlorine. Chlorine has atomic number 17, right? And it has two isotopes, chlorine 35 and we have chlorine 37 as well. Now, the abundance present here is 75% of chlorine 35 and 25% of chlorine 37. But the mass value, when we are writing down it in the periodic table, it will be chlorine with atomic number 17 and mass number of 35.5. Okay? Now, how did I get that? 35.5. This is the average value in accordance to my abundance value. Okay?
Did you do 75 times by the 35?
Yes,
And then
yes,
25
yes,
times 37?
yes. How it is calculated? It is the mass of the isotopes divided by the total mass. Okay, so it is calculated by the 75 times 35 plus 25 times 37 divided by 75 plus 25. So the value will come to 3550 divided by, which will give me the value of 30.5. Okay, so at the end we are going to use this value. You understood what is a relative atomic mass?
Yep.
Okay, so this is how we found out here. This is a simple method. Now we are going to use the same formula, same format, and we are going to apply for strontium, where we have different percentages, and we are going to find one particular relative molecular mass here. Okay, relative atomic mass here. Okay, have you finished writing it down?
Yes.
Shall I move on to the next slide, please, then?
Yeah, that's okay.
So I'll just write the values again. We had isotopes 84, which had abundance of 6%, 86, which had 9.86%, then we have 87, which had 7%, and we have 88, which had 82.58%. So these are my isotopes number and these are my abundance. Okay, so how am I going to calculate it? So this will be AR will be, just multiply with everything here, that will give me 84 times 0.56 plus 86 into 9.86 plus 87 into 7 plus 88 into 82.58, and this will be divided with 0.56 plus 9.86 plus 7 plus 82.5. denominator will always be 100. Okay, if you add, you will be getting the value as 100. So if possible, try to solve this and tell me the answer, please.
Okay. Yeah, 87.7.
Altogether,
That's the final answer.
the final answer. Okay, good. So 87.7 you said.
Yes.
So that will be this way. So my answer will be 87.7. So my final value, that is my relative atomic mass of strontium, will be 87.7. You got how we got the value? You said we have to put 82.58, right? Because
Yep.
but when we took out the value or the average value, what did we get was 87.7. Understood this? What is happening?
Yes, I've understood it.
Okay. I'm just checking whether I have left anything or not. Okay. Is there anything other than this, what you have done in school regarding time of flight?
We've also done time of flight, like maths questions to work out like the length of the flight tube or the velocity or the mass or the kinetic
Okay.
energy.
So you all have done it in the detailed form.
Yeah.
Okay, this part you're clear. So moving on, we'll see. We were talking about energies, right? We saw kinetic energy, we saw acceleration, mass change, and all. So we'll go more into.
Okay.
Now there is potential energy. Now, what do you understand by potential energy?
Um, not really sure the difference.
The ratio of the
Is it the ratio of 9 to 6 to 1?
it's not
Is that
it's 9 to 6 to 1. Okay, in general, tell me what is a potential energy. Not going into very chemical detail, chemistry form of detail. In general, tell me what do you understand by a potential energy?
potential energy is like As in like the stored energy.
Stock. Oh,
Stored energy.
okay. I'll give you a good example of potential energy. Okay. Have you seen dams anywhere?
Yeah.
Okay. What is the concept of dams?
The concept of a dam is to store water.
Store water from
Just from like the village or the city where the river flows through.
okay, from somewhere the river is flowing and they are storing this water. Why are they storing this water?
So then the village or the town or city doesn't flood.
Okay, that means okay, they don't get affected by floods, and later, in case these places need water, they will supply, right? Through these dams. They will release the dams in a small quantity of a time, right? Now,
Right.
if this is the dam this way, this is the wall, okay? This is a big wall over here. Now, here they have the source of water, right? Now, this water have been coming from the rivers and they have stored here, okay? Now, this water is under great pressure. What great pressure? First of all, it is above the gravitational force, right? It is above the sea level. We have a sea level and it is far above the sea level, right? So it is working against a gravity here. Hello? Hello?
Yes. Sorry.
So what I was telling was this force of water, it is above sea level, right?
Right.
Okay. That means it is working something against the gravity. Okay, first thing we saw, it is working against gravity. Second, it is just waiting, or how shall I put my sentence? Okay, it is under a force that once it has been released, imagine these are the opening or the outlet and they are released. Will they flow very smoothly from the from the dam, from the openings?
It'll be very fast because of the pressure.
Fast pressure. They have high pressure. They won't come smoothly, but they will fall under great pressure, right? So this is potential energy. Potential energy which is acting against gravity and it has lots of pressure in it. You understood? This water has a high amount of potential energy that is just waiting to get released. Okay? It's all clubbed together. It's like waiting when to get released. Okay? So this is a potential energy. If I need to put this potential energy in terms of chemistry, potential energy, we are talking about a charged particle. Okay? Potential energy of a charged particle in an electric field is related to the charge of the particle. I'll write the definition over here. I'll mention this is potential energy. Okay? Potential energy of a charged particle in an electric field is related to the charge of the particle and to the strength of the electric field. Okay. Now, how it is related? It is related to the charge of the particle. Charge of the particle, I can relate it to the pressure. It has a good amount of pressure right here. So it has a charge over here. To the strength of the electric field, gravity, it is holding it, right? The strength it is holding it against the gravity. So that is the strength of the electric field. Understood? And here we have an equation of how it is expressed. Potential energy is equal to QU. Now EP is the potential energy, Q is the charge of the particle, okay, and U is the electrical potential difference. Okay, electrical potential difference, or in simple terms it is also known as the voltage. You understood this potential energy?
Yes.
Yes. Okay. So this was potential energy. Now what is happening? Now I have released this dam. I have released the outlets. It's flowing down, right? Now this will have acceleration, the speed. Okay. What is happening here? All of this potential energy which was stored over here, it comes down, or it is converted to kinetic energy. Okay, kinetic energy released down with a great force, with the gravity is moving for the gravity, and it is coming under pressure. Okay, so what can we say is, when this charged particle, we are talking about the charged particle, is accelerated into the time of flight mode. Okay, it is accelerated in the time of flight mode. What is happening? It is converting itself into kinetic energy. So I'll mention this way. Charged particles therefore potential energy is getting converted to kinetic energy. Okay, this was the equation for potential energy. And now kinetic energy is expressed as Ek to half mv square. Okay, mv square, where m is the mass and v is the velocity. Clear?
Yeah, clear.
Two different values here, one for potential energy, one for kinetic energy. Yes, but
Yes.
according to the law of conservation of energy, potential energy is equal to kinetic energy. Am I right? It has just been converted, right? The whole water
Right.
is the same. It is the same water which is stored here, and it is the same water which is flowing down. So basically both are same only. Even energy is same. Here it is termed as potential energy because we are storing it, because it is working against the gravity. Here it is releasing, it is flowing along with the gravity. So only thing is they are just getting converted, but nothing is going to change with their energy. So we can still write it as potential energy is equal to the kinetic energy. Okay, when we write this, that means our equation should also be same. That means UQ will be equal to half mv square. Right?
Okay. Right.
Now we are talking about the velocity. See, velocity we have mentioned here. Now this velocity of the charged particle after acceleration means when they are moving, will not change because it is moving in the time of a flight tube. I have mentioned here, charged particles are accelerated into time of flight too, and therefore it is not going to change. Okay, velocity, we have two kinds of velocity, initial velocity and a final velocity. So this is not to change. Okay.
Okay.
Okay. So now what is happening here? This we have to convert it into a digital converter. So velocity, we can put it as d by t. That is distance upon time. Fine.
Right.
Velocity is distance upon time. Now what are we going to do is, we are just going to put the value of v from here. So this will be qu equal to half m d by t the whole square. Okay, so I am
Okay.
everything. What do I want is the time of flight. Where is time? Time is over here. Okay, so if I need
Okay.
my square brackets, the value will be d square upon t square, right?
Right.
So I want the value of t. So t square, if I rearrange everything, this will be d square m divided by 2u cube, right? I've just taken my t square side, and if I need to find the value of t, I have to put a square root sign. So if I put a square root sign, my answer will be d root 2u and whole root of m by q.
Okay.
Okay,
Yes, I understand.
square roots. Okay, we get the time yielded. Now, why have I written this two separately, and why have I not put into the one whole thing? Now, this value, that is the distance divided by the root of 2 and u. What is u? It is a voltage, right? This contains a constant. Okay, this whole value, it contains a constant, and this constant I am going to denote it by the term k, a small k. You understood what is happening?
Yeah.
Okay. So now my value will be T equal to K root of mass divided by the charge of the particle. Basically, we will be getting this constant value, the value of K. Okay. That is why this by a single term K, which is mass divided by the charge of particle. Understood till here? The relation
Yes.
potential energy and the kinetic energy, and how have we derived the time factor, time of flight mode? Yes.
Yes, I understood this part.
Now just go through the entire thing what we have done today, and if you have any doubt regarding anything what we have done,
I don't have any doubts today.
so till this part it is clear.
Yes, it's clear.
Yes. Okay.
Yep.
Since we are about, it's only 2 minutes left for our class to finish, I don't want to start with the next continuation topic. Okay,
Okay.
what I'll do is, let me find if I have some homework. You do that for your homework part. Okay.
Okay. Is it just these three questions?
Yes, I'm just looking at them.
Okay.
also has the graph value. So it's okay. Okay, I have one more thing. Okay, I'll give you this one. The continuation of this question, I will put it down here. Okay, this is the continuation question of this part. So just take a screenshot of it or something like that. Try to answer them, okay?
Okay. Thank you.
Thank you.
Hello.